let's have a look then at a very important idea in astronomy, which is, that's a very grand name indeed, the Hertzsprung-Russell diagram. Okay? Which has a very grand name because it was it was invented by two people at the same time. Mr. Hertzsprung and Mr. Russell invented this diagram. As I understand it, independently, they didn't work together, but they both came up with this idea around the same time, hence they both got their name on it. Okay? It's sometimes shortened to the HR diagram. Okay? And it's basically a way of organising stars and thinking about things like the evolution of stars. Remember the nebula, main sequence, red giant, white dwarf thing. Organising that in basically a graph. Okay, so the Hertzsprung-Russell diagram is a great big graph we can use to organise stars. That's a good way to think about it. Okay, now up the side goes. I always like to think of this is to imagine the star is like a light bulb. All right, which is fairly reasonable. Star is a light bulb. On light bulbs, you sometimes have power ratings. It says this is a 100-watt light bulb, it's an old-fashioned one, or this is a 10-watt light bulb, it's an LED or something. Now, what does that tell you? Well, that number, as you know from your physics in watts, tells you the amount of energy per second coming out of the star, what we call the amount of power. All right, it tells you its power rating, and if you have bought light bulbs, you might say, I want one with a 60-watt power rating, and it tells you how quickly it chucks energy out, which in simple terms means it tells you how bright it is. Okay? And that's what goes up the side. Up the side of the HR diagram is the power output of the star. Okay? How do we refer to this in astronomy? You can refer to it as luminosity. Yeah? The luminosity of a star is generally taken in astronomy to mean the power output. You'll remember the magnitude system. Yeah? Magnitude of a star. But which one do we need here? Remember there's two types of magnitude, isn't there? Apparent and absolute. We need up the side here, we need absolute magnitude. Alright, capital M. Apparent magnitude won't do, and that's why the other thing we don't put up the side here is brightness. What's the brightest star in the sky? Is that because it's the most powerful star in the universe? No. Because it's very close, isn't it? All right. Brightness will not do because it is too vague. All right. Apparent magnitude, little m, will not do because apparent magnitude of something, take for example the sun, which has the highest apparent magnitude of anything, has got nothing to do with its power. It's because it's very, very close. All right. So we can't have anything to do with distance up the side. We want, go back to the light bulb, we want the actual true power rating, okay? And so you can have power rating if you want, you can have luminosity. This isn't very common in astronomy because, of course, think how many watts a star is. It's just some phenomenal number. So this is correct, this is true physics, this is right in your head, but we actually don't often use it because power in watts is a bit cumbersome to use. We use luminosity or we use absolute magnitude, okay? The value on the magnitude scale if the star was 10 parsecs away. We don't use anything that involves distance or anything that's a bit vague and it could involve distance. All right. If you're asked about these in the exam, these are the two words you don't want to use. Okay. At the top here, then, you can think of it in really simple terms. You're going to have very bright stars, and down the bottom here, you're going to have very dim stars. Okay. But be careful what you say. The brightest star in the sky, well, that's the sun. We don't quite mean brightness, do we? We mean the actual power output. We don't mean the brightness as it would look in the sky from Earth. Okay? Now, along the bottom is the tricky one because there's various ways of doing the bottom axis. All right? And if you look in different books, you'll see different things along the bottom axis. Okay? What we basically want to do along here is, I think the easiest way to think about it is the colour. Okay? Colours of stars, red, orange, yellow, green, blue, indigo, violet, whatever, different colours of stars are arranged along the bottom axis, okay, following the spectrum red, orange, yellow, green, blue, indigo, violet. In simple terms, that's what we're doing along the bottom axis. We're arranging the stars in order of colour, okay? Now, why would we want to do that? Why is the colour so interesting in astronomy? Well, because the colour for very hot things is linked directly to temperature. Now, this is a piece of physics which, again, a bit like radiation pressure, we just need to take a moment to think about, because it's not a piece of physics you come across in everyday life, okay? Radiation pressure inside stars, light pushing outwards, is a bit of a mad thing. It's not something you see around you like gravity, but on a much bigger scale. It's a totally new piece of physics. And this here is not something you come across every day. This is a very important piece of physics, and it relates to very hot objects, okay? Objects generally hotter than anything you would come across in your everyday life, with a few exceptions, okay? When objects get very, very hot indeed, then their colour becomes linked to their temperature, okay? Now, if you look around the room, you can see, if it was on the camera probably can't, but you can see there are things that are blue, there are things that are sort of horrible yellow colour, all sorts of things that are purple. And why are they different colours? Is it because they're at different temperatures? It's not, is it? What makes things blue or red or green is normally because they've been dyed. They've got different chemicals in them that reflect the light differently, and that's why this pen looks blue and my tie looks purple. It's just not something that happens in everyday life. In everyday life, colour is linked to the chemicals you're made of, how your surface is done, etc., etc., and that's not what we're talking about here. In astronomy, we're always talking about things which are thousands and thousands of degrees, okay? If we took everything in this room and raised it to 10,000 degrees, would its original colour be preserved? Probably not, okay? But for very hot things like stars, colour links to temperature, okay? In, again, a rather surprising way. Things that are relatively very hot, only just very hot, are red. And things which are very hot glow yellow or orange or whatever, and things that are extremely hot glow violet or blue or something like that. Okay? So the bluey violet end is the very hot end, the reddy orange end is the slightly cooler end, but here you would be talking still, I don't know. Well, let's put the sun in, okay? The sun's sort of in the middle somewhere, and the sun is a sort of an orangey yellow colour, okay, more yellow than orange, I guess, and for that reason it's a sort of middle temperature star. How do we know the sun is a middle temperature star? With a surface temperature of about 6,000 degrees, given that no one's ever been there. How do we know the sun has a surface temperature of about 6,000 degrees? The answer is because when you look at it, its light has this characteristic yellowy colour, all right? If the star appeared red, like the sun appeared red, then we would say it's perhaps only 3,000 degrees. And if the sun appeared a bright bluish colour, we might say it's 10,000 degrees or something like that, okay? So in simple terms, the colour of something like a star tells you how hot it is, okay? Now, where does human experience start on this graph? There. Yeah? Do you often come across objects which are so hot that they're red? Well, the one I always think of is if you took a piece of iron, you took it down to the forge in the DT, and you put it in the forge and heated it up, like in a blacksmith's thing. If you heat it up, what colour does the ordinary black metal go? It starts to turn red. Can you imagine heating a piece of iron so much that it melted? What colour would it be? Do you see? Have you ever seen like a steelworks where they show all the iron, molten iron running through channels and things? It's always that colour, isn't it? It's an orangey colour. Orange is fundamentally hotter than red. Now, the big confusing phrase in the English language is the phrase red hot. And things, if you're a human being, which means you live over here, yeah? Things that are red are very hot, and if you touch them, you will hurt yourself. But you could make them even hotter, and they would glow orange. You could make them even hotter than that. They'd glow yellow and green and blue and violet and so on. Okay? And there are stars in the universe whose light has a very bluish violet colour to it, and we know that's because they're at much higher temperatures than the sun. They're at tens of thousands of degrees. Okay? The sun's a good reference point, sort of orangey yellow is characteristic of about 6,000 degrees. If you see molten iron at about 6,000 degrees, if you see molten iron which is an orangey yellow colour, it's generally because it's at that temperature. Okay? You don't see that very often, but if you go to a steelworks or somewhere, you might see that. Where do you see things at this temperature? The only thing I can think of is lightning. Air doesn't conduct electricity, so when a lightning cloud forces it to conduct electricity, the little bit of air in the channel that the lightning forms in, for a brief fraction of a second, gets heated to tens of thousands of degrees. Do lightning bolts look reddish in colour? Orange? Yellow? Blue? They do, don't they? And it's because there isn't as much energy as you'd expect, because of course how many atoms are there actually involved? Not very many, because it's just air, isn't it? But those air atoms are actually getting to that kind of temperature very, very briefly, and that's why the light that's given out has the characteristic bluish colour. All right. If you look in books or on the web, you can find much better ones that have like a pretty rainbow along the bottom with colours in. Much more elegant than my just writing it, but the idea is the same. Okay? So along the bottom you put the colour of the star. Why? Because the colour of the star tells you its temperature. The colour of a board marker doesn't tell you its temperature, and the colour of a tie. What does this tell you? The purpleness and the blueness. What does this tell you about their temperature? Nothing. Because they're over here in the world of things that are only like 20 degrees. Here we're talking things that are at least, I don't know what the minimum temperature is for a star, but it's something like 3,000. Once you're below that, you're not a star. Okay? So just be careful with this piece of physics, because it's something that you don't come across in everyday life. But think of molten iron. Think of iron getting hot, iron melting, things being vaporised like in a lightning strike, and you'll see the increasing pattern of colours. Okay? And it's really important because, of course, we can look at things right on the other edge of the universe and say, right, that star appears the same sort of bluish colour. It must be at this many degrees. That star's got that nice orangey, reddish, yellowy colour. It must be the same temperature as the sun. Okay? If there were different chemicals inside, if someone had put a box of board markers into a star, wouldn't make any difference, would it? It would all be vaporised and it would all still have the same colour and temperature. Okay? Now, what do you notice about the temperature axis then? Yeah, it's backwards, isn't it? You see, this is the hot end and this is the cool end. Right? So the spectrum goes backwards, red down to violet that way. Very importantly, you can think of it as a luminosity temperature graph. All right, if you want to sort of zoom back from all this nonsense, and in real physics terms, what are we drawing here? We're drawing a luminosity temperature graph, okay? But if you do that, you need to be very careful, because traditionally in physics we draw quantities increasing, don't we? And temperature is along the bottom, but it's the wrong way round. Hot stars would appear on this side of the line, and cool stars up there, okay? Now, there is another way of defining this, okay? Astronomers don't really classify stars by colour. Although I've talked about red stars, yellow stars, orange stars, blue stars, obviously astronomers need to be a bit more precise about this, and so they use something called spectral class. Okay? You might look out with your constellation photography, and so I photographed Orion. Look at that nice red star in the top corner there. Look at that blue star at the bottom. That's fine. But in proper astronomy, you would actually want to be a bit more precise. What particular shade of red, what particular shade of blue, a bit like a sort of a cosmic... Have you ever had those charts for choosing paint colours? It's a bit like that. There are shades of orange, aren't there, going into yellow? If you don't believe me, go into B&Q and get one of their paint things. They've all got silly names, haven't they? There's different shades of yellow, orange ending up eventually in yellow, and there's different shades of red going off into orange and so on. Okay? And in proper astronomy, you would need to be more precise about this. So what we do is to give each star its own spectral class. Okay? Yes, the sun is a particular shade of orangey yellow, or we need to define that particular shade. And the way we do it is with this sequence of letters, which I'm about to get in the wrong place. W-O-B, A-F-G, K-M-R-N-S. W-O-B, A-F-G, K-M-R-N-S. Right? That's the sequence of spectral classes. Okay? Now, the good news is it's not actually introducing anything new. It's just a more precise way of talking about colour. All right. So this bottom axis, you can put stars in order of colour, you can put them in order of temperature. That's actually the same thing when you're this hot. And you can also put them in order of spectral class. All the orange-yellow stars are in a particular spectral class. All the red stars are in a particular class, and so on. It's just, if you like, subdividing. Think of it like a paint chart. It's not just, if you went into B&Q and they had red, orange, yellow, green, blue, indigo and violet, you with me? That wouldn't work, would it? Because somebody was, I wanted a colour that was a bit more orangey and a bit less yellowy. So what do they have? You ever been to the paint department of a DIY store? They've got, haven't they, all kinds of oranges, about 17 different kinds of orange, all drifting into yellow and so on. And that's really what spectral class is doing, okay? How to remember this, because you need to remember this for the exam, okay? Very easy sentence to write down. Wow, oh be a fine girl, kiss me right now, sweetie. Not a phrase you hear very often, but for that reason it'll hopefully stick in your mind. Wow, oh be a fine girl, kiss me right now, sweetie. Okay? That rather silly sentence is a good way of remembering the sequence of letters. Wow, oh be a fine girl, kiss me right now, sweetie. All right? And the W, O and B stars are the very hot blue stars. I always think of the B for blue. And can you see the other one down the other end? Let's just move that to make that a bit clearer. K, M. Can you see the two letters that help you to get it the right way round? It's the R, isn't it? Can you see? Look at the R and look at the B. B for blue, R for red. Get it? They don't actually stand for those things, but it's just a handy way of doing it, all right? But if you write it along the bottom axis, and remember that temperature goes backwards, then you'll have it right, okay? They do have a sequence of numbers from 0 to 9 in between each one. So how many different spectral classes are? There's this many letters, but within each one, how do you get from being W to O? You go W0, W1, W2, W3, W4, W9 becomes O0, O1, O2. Do you see? So there's 0 to 9 in between each of these. So I can't work it out in my head, but there's an awful lot of them. And this way, not every single star, but you can, a bit like the paint chart, you can now have precise shades of orange and precise shades of yellow. Okay? The sun, I've kind of gone a bit wrong. Oops. The sun is a G2 type star, all right? Slightly off of G. Okay, so 2/9 of the way along from the letter G, okay? And that makes the sun a G2. You need to know that, I think, if you're looking at specification. All right. What does G2 mean? Orangey yellow. A particular shade of orangey yellow. And this is the really powerful thing for astronomy, because you think, why are we doing this? Is because you could look out into the night sky at a very distant other star and say, gosh, look at that. That's exactly the same spectral class as the sun, which tells you its temperature. You can say that star will have the same around about 6,000 degrees surface temperature as the sun. Okay? So spectral class and colour, I always think, are closely linked. Spectral class and colour are linked in the same way that a set of colours on a paint chart. All right? There are these basic colours, but we subdivide them into different shades. That's what spectral class does for colour. And the very important piece of physics here is the link between colour and temperature. These temperatures mean these colours mean lowish temperature for a star, and these colours mean higher temperature. All right? Be careful with this one because it isn't very much close to things you see around you. As I say, you live in a world at a temperature where 3,000 degrees is awfully hot, and most things around you are way below that, so that their colour has nothing to do with their temperature. All right? So this is the one that takes a bit of thinking about. Okay? Is everybody happy with that? Right. Now, what we can do, which could take a very long time, I've got an activity where you can do this, we can basically put every star on. So we can take the sun's sort of G2, orangey yellow, and it's 1 sun power. Okay, so let's just have that as equal to the sun, whatever luminosity the sun might be. Its absolute mag is 4.5, isn't it? +4 or something. Anyway, here's the power output, or the luminosity, or the absolute magnitude of the sun. That goes there, okay? And what you can do is just go through the whole sky. You can go through the whole sky and you can plot every star. There are some stars hotter than the sun. Which way do I move my pen? There are some stars which are cooler than the sun. Get it? There are some stars more luminous than the sun, and there are some which are less luminous. Okay? So we could go through a few thousand million stars and plot them all on this diagram. The important thing about the HR diagram is that every star has its own unique position. Okay? Now let me fast forward this next bit where I plot 10,000 million stars, because what you find is a very clear pattern. Sometimes it's drawn as a curve, sometimes as a straight line, but basically you get a big pattern going top left to bottom right. All right? The vast majority of stars live in that line there. You get a few stars down here, and you get a few stars up there. Okay? Now, this line across the middle is called the main sequence. Okay? So across the HR diagram is the main sequence where the majority of stars live. Okay? Now, from that we conclude something about the evolution of stars. You'll know the sequence, won't you? From nebula to main sequence to red giant to white dwarf, etc., etc. Well, how would we know how long a star spends in each of those phases? Has anyone ever seen a star go from being a main sequence to a red giant? It just never happens, does it? Human evolution, we've talked about before. The evolution of birds and animals and fish and people takes a long time. So much so, as it wasn't until the 19th century that scientists worked it out. But think how long the evolution of stars takes. It takes longer than the lifetime of the Earth. That's just nuts, isn't it? So think about it. It's an interesting area of science where we're talking about changes and things evolving that we can never see. You can go and dig up fossils and stuff like that and kind of reconstruct the evolution of humans, and that's quite difficult. This is practically impossible. As I've said before, if you had your life compared to the life of a star, it's like the life of a person compared to a camera shutter. All right? If a star lived for 80 years, you'd live for 1,000th of a second. All right? In that 1,000th of a second, could you work out how humans change? You wouldn't have a hope, would you? Since the earliest days of astronomy, I don't know, 10,000 years ago, if we look at the records those people made on their clay tablets of the sky, what do we notice? Difference. A few stars have moved a bit, some have changed brightness a bit. That's nothing. Are there stars that we used to see as red giants, which are now white dwarfs? No. That just takes too long. It's a bit like if you went to the centre of Leeds and you took a big photograph of everybody coming out the station and you counted how many adults, how many pensioners, how many children. What would you probably find? Most people would be in the bit, there'd be some young people and there'd be some old people, most people in the middle. What could you then conclude? If you're an alien come down from outer space, you get a big group of people, you photograph them, 90% of them appear to be adults, there's a few children, a few old people. You're going to leave in 1,000th of a second. What could you conclude about the human lifetime? About the proportion of the human lifetime that you spend as a child, an adult, or an old person. So we assume from that this means that stars spend an awful lot of their life in the main sequence. Okay? Why? Because the snapshot, and even 10,000 years of human observation, 10,000 years of human observation, that is a snapshot. In the lifetime of a star, the 10,000 years that we've been looking at the sky and taking records is just really, really small. So we assume that this means that stars spend the majority of their life in the main sequence. Okay? Up here are stars with a high mass, and down here are stars with a low mass. Why do you think high mass stars are up here? If I'm a main sequence star and I'm forming out of a nebula much bigger than the one that made the sun, then I end up here. If I form out of a cloud of gas about the same size as the one that made the sun, I end up about here. And if I'm a star and I form out of a cloud of gas much smaller than the one that made the sun, they all become main sequence stars, but I'll be down here. Think about the axis. I'm a bit scribbly now. Think about this axis. If I form out of a very, very big cloud of gas, tell me about the strength of the gravity pulling inwards. It's going to be very heavy, isn't it? Remember the gravity radiation pressure balance? So if you form out of a big mass cloud of stuff, then you're going to have a lot of gravity pulling in. So what do you need to balance yourself as a main sequence star? You need lots of radiation pressure, don't you? So you have to be very bright. All right? Heavy stars are much brighter. Why? Because they have to be. If you're a heavier star, you'll have more gravity pulling in. You've got to chuck the fusion energy out faster, haven't you, to hold the star up against gravity. Okay? And the same thing works here. If you're a low mass star, then you haven't got so much gravity pulling in. You don't need to burn the hydrogen that fast, to fuse the hydrogen that fast, to hold up yourself against gravity. Okay? Now, the interesting part of this graph are the two groups over here. Okay? Let's start with this one. Use the graph to tell me two facts about stars in this region. If I'm up here and I'm over here, tell me two facts about stars in that group. They're going to be very bright and quite cool. That's a bit strange, isn't it? A very bright star, which was very hot. That makes sense, doesn't it? But a very bright star that's very cool. That's very strange indeed, doesn't it? If a star's very cool, a good way to think about this is to think about just a square metre of that star. It's in this part of the graph, which means it's quite cool. It's got colours like red, which is about the lowest temperature colour you can have as a star. It's probably only a few thousand degrees, cooler than the sun. Spectral class, M, R, N or S. That means if you had a square metre of that star, what would it look like? It would be red in colour. It would be jolly hot, 3,000 degrees, but compared to stars, that's quite low. How much energy is it chucking out? Well, not a great deal, really. It's not a particularly hot star. So think about it. Each square metre of this star doesn't chuck very much energy out. Now zoom back to the Earth, where the star is a dot. What do we notice about the dot? It's really bright. How many of these must it have? Quite a lot. It must have a lot of, you see? Get the idea? How many square metres of surface area must it have? It must have a lot of them, mustn't it? It's the only way a cool star could be really bright. Do you see? Because cool means that each square metre of your surface only gives out a relatively small amount of energy. So this star must be a giant star, because it's on that side. It's called red giant. Do you see? Okay, so stars up here are red giant stars. And we believe when stars are finished on the main sequence, they evolve into the red giant. Okay? But again, if you look at human population, how many people over 75? Not very many. What does that mean? Humans spend more of their life less than 75 than more than 75. Okay? Stars down here. Tell me two facts about stars down here from the graph. They're very hot, but not very bright. Now that's odd. The main sequence is fine. Hot stars being very bright, yeah, fine. Turn up the power on your fire, it gets hotter and brighter, no problem. Stars down here, not very bright, not very much energy. Again, if you've got a light bulb at home with a dimmer switch, try it. Turn it down so that if you've got an old-fashioned light bulb, turn the dimmer switch down so the filament isn't very hot. What happens to the brightness? It goes down. Turn the dimmer switch so that the filament of the light bulb is really hot and the brightness goes up again, doesn't it? So these don't require any explanation. These are just common sense. All right? Hot things are brighter, cooler things are dimmer. But these are the ones that are a bit strange. And the one down here has got every square metre. Now it's very, very hot. Spectral class WOB or something like that. Tens of thousands, not thousands of degrees like the sun, but tens of thousands of degrees. And what that means is it must be chucking out a lot of energy. All right, there's lots of energy coming out of each square metre. Why? Because each square metre is very hot and radiating lots and lots of energy. Zoom back to the Earth, we look at that star and we see a very dim star. What does that tell you about how many of these square metres it must have? It's not many. This star is going to have to be quite small. If it was a great big star with every square metre giving out tons of energy, it would be bright, and down here it's not. It's low luminosity. This star must therefore be a dwarf star, mustn't it? All right? So you need to be clear in your mind why this doesn't require any explanation, but this must be a giant star, obviously a red giant, and this must be a dwarf star. To be very hot and yet dim, you would have to be very small. To be very cool but very bright, the only way you can do that is to be a giant star. And as you know, that one's referred to as a white dwarf. Okay? And we believe this is the evolution of stars. The Sun, for example, will spend most of its life on the main sequence. Before that, it isn't really a star, it's a nebula and doesn't appear on the diagram. It then moves up to the red giant phase and then down and becomes a white dwarf. And for the Sun, which is below the Chandrasekhar limit, that's pretty much the whole story. Okay? But the HR diagram gives you a way of classifying stars and identifying these three. There are other types of stars, but these are the most important ones: the red giant, the white dwarf, and the majority, which are the main sequence stars. Okay? And the evolution of stars that we talked about, you can see on the diagram.